Hello everyone, this is a little bit confusing because this is stuff that I originally scheduled to be in week 5, but I had to bring it forward to make sure that you would all be good for your Taoist tests. Um, so we covered the essential stuff in a tutorial and lecture, and now you can treat this as a revision read-in. So in your previous week you should have read through this section here, all about stress is force over area. We're going to typically use a sigma symbol to represent stress. If things are being pulled apart, we call that to be in tension. If they're being pushed together, we're going to call that in compression. We measure stress in terms of newtons per meter squared. And typically things go into the millions, so we often have a mega newton meters squared. Because some engineers don't like using mega, you can then alternatively, instead of using meters squared, you could use millimeters and then make that newtons per millimeter squared. A lot of engineers like to use megapascals, which represents a newton per meter squared. Extension, when I start pulling something apart, it will tend to get thinner and it will tend to get longer. So the amount that it gets longer is the extension. That's going to be my delta L value that I'm going to have, and then divide it by the original length, and that term is known as the strain. In this particular case, it's known as the longitudinal strain because it's the amount that it's extending in the longitudinal or the axial direction. Strain will have dimensionless units. Sometimes authors write the units as millimeters per millimeters or meter per meter to represent the fact that they measured the original lengths that they were using in those units. Sometimes authors also use percentage, so they might convert strain to percentage times by 100 and then put a percentage on the end. Shear force V, okay, so V is a symbol commonly used to represent a shearing force. And what we've got here, so we've got a force being pushed down here, and so what would that mean in terms of forces on the other side? Well, actually there's a slight error here because this is going to be V divided by 2, V divided by 2. Right, so if I'm pushing, what I'm doing here, I guess the way to imagine it is that I imagine that we've just got one V component and another V component. So it's kind of an error here, really, in this drawing. And this case again, we've still got force divided by area. But often for shear force we don't use the symbol sigma, we use the symbol tau. Okay. For shear strain, so now this is where I'm going to glue something down, and I'm going to apply a pulling force. So we often use the symbol there for P for represent pulling force. And if it's going to pull and this is staying stuck, then that is going to move a certain amount x distance. We're going to take the height of the block to be L, and then we're going to measure the shear strain in terms of the distance moved in that shear direction divided by its original height. Now this gamma term can represent two things. It can actually represent the angle that block is being shifted, and it can represent the shear strain. So it can be used in two ways. You can represent it in terms of no units to represent the fact that you're talking about the shear strain value, or you can represent it and put radians on the end to demonstrate you're talking about the actual angle itself, but the value is both in either case. Poisson's ratio, don't use that too much, so I haven't really concentrated on it, but it's the ratio of when I pull something apart, what sort of percentage that will elongate divided by the percentage of something contracting either side. Now because it contracts, so that's going to be negative, and pulling apart will be an expansion, will be positive. Poisson put a minus in front so that he ended up with Poisson values that are going to be positive. So, so I'm pulling something apart in longitudinal direction here, and then the lateral direction we're going to get smaller. For us, we are only going to be studying for structurals really. Ultimate tensile stress does creep in, but we're only really studying it up to the elastic limit, and the elastic limit tells us, or the Young's modulus tells us, that if we take the stress divided by the strain, so more force I pull it, the more distance it gets extended, and so that gives me the stress over the strain equals the Young's modulus. Now because strain is in no units, and because stress has units, sigma there has units, what's a bit bizarre is that the modulus of elasticity, it has the same units as stress. And similarly, if we wanted to try and make something rotate, if we took the shear stress and divided by the shear strain, we're going to get this term called the modulus of rigidity. So that's the shear modulus. Ultimate tensile stress is the maximum load that a section can take before it just literally will snap and suddenly break in your hands. It can't take any more higher stress than that. It literally will suffer immediate failure. And that will be the maximum load divided by the initial area of the specimen. Factor of safety is measured in terms of the ultimate tensile stress divided by the amount of applied stress that you're planning to do. So basically we're working out what is the maximum stress that you can do. A bit like when you're going to buy some flu medicine, what's the maximum I can take, and we're going to just slightly have a little bit less than that, and that will be the applied stress. So a big number divided by a number not so big, maybe halfway up. So then we're going to end up with numbers like 2 for factor of safety. So 1 divided by half will give me 2. So read through this stuff here, talking about the factor of safety and the conditions that you really might want to consider in reality. Then there's some strain examples. I think we have Arnold screencasts for these, and so have a look for them. If they're not, then let me know and I will produce a video for you. Work solution, I have made a video and put it on into your week 5 folder, I think. And we have some problem sheets, and we have got some solutions. Well, Arnold's done some video casting for some of these questions. So anyway, so that was you only need to read up to 56. So certainly my tutorials and the other tutors should have taken you through a work solution similar to 6, because you were still doing your Dow's test, so that was to help you there, and encourage you to knock off a couple of these questions here. They're kind of boring because they kind of just repeat themselves. So once you've done 2 of them, you've probably done enough, to be honest. So yeah, so that was done in tutorial. That was done in tutorial. The other stuff, please read through.